Welcome to SUSECon 2025, Cloud Enablement at Scale with SUSE Virtualization and HPE Compute Scale-Up Server 3200, Tutorial 1168. Today we're going to look at the project, some observations, some evaluations, some limits, brief look at Harvester, and what do we want to do next, and a conclusion. So the project. So what do we want to do? We want to provide HPE Compute Scale-Up Server 3200 resources to cloud solutions. The Compute Scale-Up Server 3200 has excellent reliability, availability, and scalability features, such that IDC designated an AL4 availability platform, the highest you can achieve. Scalability-wise, we scale from 4 sockets, 128 gigabytes of memory, to 32 sockets and 64 terabytes of memory. You can grow the system 1 chassis at a time, 4 sockets each chassis. As you grow the system, the same OS instance remains, doesn't have to be changed. Performance scales linearly as you scale the system. Capacity, as you just saw, 32 sockets, 64 terabytes. And even that size is contained within a single rack. What else do we want to provide? We want to provide cloud solution resources to existing HPE or new HPE Compute Scale-Up Server 3200 enterprise customers. Cloud solution resources, container networking interfaces, container storage interfaces, container runtime interfaces, monitoring. All these interfaces are provided by many vendors and can integrate into the enterprise customer solutions. As an example, if a customer would like to migrate their existing enterprise solution to a cloud solution, we can virtualize the existing HPE Compute Scale-Up Server solution on bare metal to a virtual image, turn right around on that same platform and run that virtual image, and then eventually add the Compute Scale-Up Server 3200 platform to a newer existing cloud. So that's what we're demonstrating here. We've got the enterprise solution, all the functional units of the application running in the gray box. Virtualize the whole host with the application. Turn around and run that back on the Compute Scale-Up Server as a virtual machine. Now we're more capable of cloud solutions. And then eventually we can integrate that into an existing or new data center or cloud. Why do we want to do this? Well, customers are not asking for something that does not yet exist. So, and it takes a long time to offer or to develop some of these offerings. So we decided to jump ahead and develop a maximum scale KVM virtual machine and tuning and options and operations. So we also want to beat VMware. We wanted to provide greater scale with SLES15 KVM. And in the cloud, when we look at a cloud solution, all the applications must run on hardware somewhere. So if we look at 5 different execution options where the application will actually run, more than half of them use a virtual machine. So we decided to start with the virtual machine and make sure it can scale, because if the virtual machine can't scale, then the solution can't scale. So here's a diagram of different options. We have bare metal on the left, just a KVM virtual machine, which is currently where we're at, the application running it in, or benchmarks. The same application or benchmarks running in a Docker container, in a virtual machine in a Docker container, and then finally Harvester, where we have the application in a virtual machine and a Vert Launcher container inside a pod. Why the large scale? Well, there are already large scale options for enterprise serving. And SLES15 SP7 is now YES certified for 64 terabytes, 3,840 CPUs, and 32 sockets. SAP HANA is certified for 16 sockets, 32 terabytes of memory on both the HPE Compute Scale-Up Server 3200 bare metal, as well as the Amazon Web Services EC2 instance, which we strongly believe to be KVM based. How are we going to do this? Well, we're going to start by leveraging the Superdome Flex Linux kernel engineering group at HPE. They have many years experience developing the Linux kernel for scale-up platforms. And we want to apply the same intellectual property or technology that was developed for the Linux kernel to the KVM platform. The way we're going to go about this is deploying increasingly larger virtual machines until they fail. Primarily, they usually can't boot. So then we identify what happened, fix the failure, or identify the failure, fix the failure, and then make a bigger one and find out what the next limit is. And then rinse and repeat and keep going until the maximum hardware capacity is reached. During the project over the last 5 years, the hardware has increased. So originally we were working on a platform with 32 sockets, 1,536 CPUs, and 12 terabytes of memory. We had access then to a 32 socket, 1,792 CPU, 48 terabyte system. Then a 32 socket, 3,840 CPUs, 32 terabyte system. And finally, where we're at now is a 32 socket, 3,840 CPUs, 64 terabyte system. The test plan we're using, just briefly mentioned, is does the virtual machine boot? We had many instances in the beginning where we couldn't start it, or we could start it, but it never quite got to a boot image, or it would start to boot and fail. So the first test was, does it boot? Second, once it boots, what does it look like on the inside? So we're configuring from the outside, and what does the operating system see when it comes up? So we look at LSCPU to see what the threads, cores, and socket configuration was, and does the thread, core, and socket match for the virtual CPU match what should be on the physical CPUs. We also look at memory to see how much memory is available in the host with free -G. Then once we see that the inside looks okay, then we start saying, well, can we run some benchmarks, some Pharonics benchmarks as our primary start. And when the benchmarks could run and we had time, can we run benchmarks in the virtual machine, and that's the same benchmark on the same bare metal of the same host, and compare the performance. We've also divided up between legacy and UEFI virtual BIOS. And since the HPE Compute Scale-Up Server 3200 scales linearly, we decided now to start trying to do some benchmarks comparing the scaling from 4, 8, 12, 16, and 32 sockets. Again, virtual to bare metal. This is a lot of data. And we've started looking at, or we have briefly looked at the plots to visualize the benchmark results, and you'll see an example of that coming up. We want to move past Pharonics into some more application-specific benchmarks, and all along the way, constantly tuning the solution, constantly tuning the solution based on the benchmark results too. So along the way, we've observed a few things. First, the system does require some support resources for the virtual machine. We tried to configure a virtual machine for the whole system and ran into several issues. One example is memory in huge pages. At one point, we allocated too many huge pages on boot up, and the host never came up. We used up all the memory for huge pages, and there was nothing left to keep track of the huge pages. So now we calculate the huge pages we're able to configure for the host based on the free memory of the system running with just the OS run. Timing considerations. At one point, we tried to boot we could boot a virtual machine with 42 terabytes, but it took 5.5 hours to boot. That sounds disappointing, but at the time we were so excited that we could boot a 42 terabyte virtual machine. And we were willing to wait the 5.5 hours to see if it finally came up. Several fixes have happened since then, and now it only takes about 30 minutes to boot a variety of virtual machines, and we have actual timing for 64 terabyte 32 socket, 3,840 pin vCPU UEFI virtual machine that takes 16 minutes to boot. And that's not bad because it takes 10 minutes just to boot the bare metal host with the same operating system. We wanted to use an interface in a user interface and not just create XML code, so we were using the virt install command. And with 1,028 pin vCPUs, that was okay. When we went to 3,840 pin vCPUs, because of all the command line options, we overran the command buffer. So now we use a virt install command to create the numa configuration for 3,840 vCPUs, and then we run a tune.sh script we created to do the actual pinning based on the host that it's running on. When we started testing without numa, we were growing the memory and we got a trip up at 8 terabytes, and we found out later that there's an 8 terabyte limit for a single DIMM slot for a virtual machine. To get more DIMM slots, you need a numa configuration. So you'll see later on there's an 8 terabyte virtual machine result, and that's because of that single slot limit. The HPE Compute Scale-Up Server 3200 comes with HPE Foundation software, and in that there's a GR-systat command for graphics systat. One of the things we found is we tried adding emulator threads. Because we have 32 sockets, we're using core 0 on every socket for the host and for overhead, and we tried to add 16 emulator threads to ease the load on the system as it was coming up. It only accepted 8, but with GR-systat, we were able to see all 8 threads were active in bringing up 3,840 vCPUs. We also found that initially, due to based on another document, we were allocating the 2 threads on two threads on 2 different virtual CPUs to 2 threads on the physical CPUs, so they could use either one. Turns out when doing this, mostly thread 0 was used, so our CPU utilization was down to about a third. We switched that over to map the virtual CPU core thread socket to the physical CPU core thread socket. And with GR-systat, we can see that the workload is much better distributed. Now we can better see, as I just said, what's going on. And here's an example. So this is a display of a virtual machine running the benchmark on 3,840 CPUs. You can see it all blocked by socket. The light blue on the left side of each pair is core thread 0. The dark blue is thread 1. A lot of activity across all of the processors. This is visible with GR-systat. Evaluations. So normally during our testing, we always had something to fix, some fix to test. And anytime we got a chance to add access to one of the big systems, we were testing fixes. But at one point, we had a brief moment where we had no fixes to test, and we had some system time. So we ran a simple set of Phoronix benchmarks on the host. We ran it in the partially tuned virtual machine, and then rebooted and ran it on bare metal. We put all the results into a spreadsheet, and we normalized the results such that we divided both the bare metal and the virtual machine results by the bare metal, giving us a 0% difference for bare metal results, and the virtual machine would then show a performance difference as a percentage. We also had to allocate that for Phoronix, some of the differences were orders of 10, some were orders of hundreds of thousands as far as the results. And in some cases, a smaller number was better. In some cases, a bigger number was better. So we adjusted everything to create a plot. And while the plot isn't clear, the details, because there was a lot of information, what we can see when we go to the plot next is that above and below 0 is the performance difference between the virtual machine and the bare metal. And we can see that in some cases the virtual machine does perform better. What test was running? Why? What do we need to change? We don't know yet. This was just a simple chance to grab some benchmarks and compare bare metal to virtual. So the limits. So as briefly mentioned, we started 5 years ago, January 8th, 2020, to extend KVM virtual machine scale. Started at 4 terabytes and 240 vCPUs. Took us 5 years, and part of the key was to beat VMware. Now, we have tested SLES15 SP7 beta. We did verify January 3rd, 2025 that we can run 8 terabytes with 4,096 vCPUs. That's a single DIMM slot, and we can overcommit CPUs in that configuration. Using NUMA, we can no longer overcommit vCPUs, so we're limited to 3,840, but we can go to 64 terabytes with the NUMA configuration. And then when we look at more of a performance where we're allocating resources for the OS, more resources, we're looking at 61 terabytes, 3,776 vCPUs with the configuration. The machines that we just mentioned did boot, and we did run some brief benchmarks just to see if they would complete. We still need much more detailed benchmarks of KVM versus virtual, apply some tuning, but that system is very hard to get onto. So we're all set up for the next time we can access it, but it may take a little while. But also important here is that because we could take the beta code, or the beta code is released, and create those virtual machines, we now have the process to create the XML that creates the virtual machine. So this is the process we've broken it down to, is we'll use virt install to start the virtual machine. Tune.sh, a script we have that we actually edit the XML and run the script to create all the vCPU pinning and emulator threads and IO threads and all the tuning, what kind of tuning we'll call it, to the XML, and then that's what we'll actually start. So we have kind of a process to create a scalable virtual machine that we can benchmark and make adjustments to the process. So jumping out for a minute, what is Harvester? Well, Harvester has, in the beginning, we talked about some of those cloud resources for HPE Compute Scale-Up Server 3200 servers, the Rancher ecosystem. We have found that Harvester can create a 4-socket virtual machine, and we're currently running Harvester as a single node cluster. So we have a single Compute Scale-Up Server 3200 running a Harvester cluster that we can create 4-socket virtual machines in. We also have learned that the tools that we have, the storage, networking, load balancing, will influence the XML that Harvester creates for the virtual machine. Here's kind of a diagram of all the possible influence to the virtual machine, all the tools that would be available to solve Compute Scale-Up Server 3200 solutions using Harvester. So what do you want to do next? Seems logical. Let's combine the two. So as mentioned before, now that we have all of our changes, current changes in SLES15 SP7, we no longer have to apply community changes to the release candidates or the released code. And our current limits are physical hardware. We've also, as previously mentioned, we'll call it XML, intellectual property, performance, and scale. So we've learned how to create the XML that we want for the full-scale virtual machines and the tuning and some of the development. And we've recently learned that it looks like we can use the Harvester hook sidecar feature gate to apply the tune.sh file, and we still need to see what that looks like running in Harvester, but we may be able to jump ahead and accomplish some things that way. But then finally we considered that, since mentioned earlier that the compute scale-up server 3200 scales linearly from 4 to 32 sockets, and Harvester can create a 4-socket virtual machine, then maybe we should target that effort, that we can create a Harvester 4-socket virtual machine and use our VM scaling process to create a 4-socket machine and compare the two. Another option or another consideration is if we consider a common enterprise solution that was previously mentioned, SAP HANA, 16 sockets, 32 terabytes. We're including 4 NetWeaver nodes is the configuration for an ML4 benchmark configuration back on the certification slide. We might have a diagram like this, where we have the bare metal SAP HANA, we have the bare metal NetWeavers in the configuration. If we use Harvester to create a 4-socket version of this, so SAP HANA 4-socket, we'll consider the NetWeaver applications just for reference in the next diagram, but that's really not the focus at the moment. And then we'll use Harvester tools to build the SAP HANA virtual machine, again with the storage, networking, security, and monitoring. We might have a diagram that looks like this, where we have all of the tools influencing the SAP HANA virtual machine in 4 sockets. Again, going back to Harvester tools influencing the XML, there'll be a slightly different perspective coming up, that the Harvester will create a reference XML file at 4 sockets that we can compare to the VM scaling results. The XML for the Harvester will include definitions to connect the virtual machine to Harvester tools, the storage, the networking, and it'll also supply stuff for the Vert launcher container for our consideration. So again, here's matching the previous document somewhat. We have all of the Harvester tools creating XML to create our virtual machine. So as part of the next project, now if we start looking at it from a more common thread, Harvester's creating a 4-socket capable virtual machine, or 4-socket virtual machine. Harvester has buttons we can push to see what happens to the XML, good or bad. And resulting, we can, through several iterations, create a good baseline for comparison. On the same thing, if we go with the VM scaling XML, we can apply the knowledge we've gained in scaling to the full size to a 4-socket with the tuning that we know for benchmarks. Excuse me. And that leaves us with what's the difference? So we call it the XML investigation. What are the common entries between the 2 sets of XML? What improvements do both XMLs provide for the other? And then, since the VM scaling wasn't doing SAP HANA but was doing a Phoronix benchmark or some other benchmarks, perhaps we can shift the Harvester over to do the same benchmark image. So we're now benchmarking the same, running the same benchmarks in both environments. And again, based on all of this, maybe there's some changes to Harvester that would be preferred not only to assist the 4-socket solution, but allow it to scale to 32 sockets. So this is the diagram we're working from then. So we have, on the left side, we have Harvester creating XML for a 4-socket, and we have the VM scaling XML that we can move over. And what do we need to do in between? How can we adjust that? So the conclusion. So there's a question mark here. So our target, based on everything you've seen so far, is to run an application-specific benchmark. So for example, SAP HANA ML4, and configure one of them all bare metal, like we saw with the 16-socket 32 terabyte, and create one all Harvester, So harvester, we push the buttons and it creates a solution. So what's the maximum size? What do we need to do? And hopefully we're up to the maximum size by then. And then the final result is to plot the results. Again, what we showed is the performance difference, positive or negative, and what can we tune. So finally, or on top of that, this isn't a conclusion, but a beginning. So when we can do everything with the target, now we have a tool to evaluate new hardware, new benchmarks, because Harvester should be able to just deploy it. We'll run against bare metal, and we'll be able to do it with bare metal also based on the process. Regression testing as operating systems are updated and new versions of the operating systems come out. And then, of course, new Harvester features. What does a new Harvester feature provide, and how can we benchmark that against the bare metal? So this is kind of all the work we've done boils down into roughly this diagram. So we have at the top left, we have Harvester creating the large maximum size virtual machine solution that will then process through benchmarks to create an output plot or surface map. We may end up with a surface map because there's so much data, and that's the end result. And it may take a while to do it, but that's what we're looking at. So any questions or comments, feel free to send them to me at payton, P-A-Y-T-O-N, at hpe.com. Thank you.